Well, isn't it nice to be here? Yeah. My God, it's been a long time. You know, I haven't taught a class in person since March of 2020. Great. People exist. It's amazing. This is about where we were, if anybody remembers, right? Yeah. All right. Announcements. Obviously, you all found the room. So what we're going to do from now on, now that things are, you know, the F4, now that things are going to be in person, Manav right there is going to be recording the lecture. We're going to be posting it to the YouTube channel upon completion of the, you know, at some time this evening. And hopefully the quality comes out good enough that it's useful. If not, we'll try to improve it. But how are y'all feeling?
Good.
Good?
How are you?
I'm doing okay, thanks. Yeah. Oh my goodness. So, I know it's weird. I feel like I'm talking to you guys for the first time, you know. But yeah. Well, anyway, we were talking about programming. We were just about to talk about the factorial, and we were going to do a couple of implementations of that. So, everybody could please follow along. So, factorial, right? Who can tell me what the factorial function does? Anybody? There we go.
It's like n times n minus 1 times n minus 2 times n minus 3 all the way to 0.
Yeah. You take all of the natural numbers up to n, you multiply them together, you get the factorial. What's it used for?
Pass.
Anybody?
Permutation?
Permutations. Yes, very good. So it's a relatively simple function to calculate using a computer, but it's a little bit, you know, complicated if you're going to do it by hand. It's a little bit, you know, involved. So it's kind of an ideal candidate for writing an algorithm. So that definition once again, n factorial, if n is equal to 1, or sorry, if n is equal to 0, then the factorial of that is 1. And there are good mathematical reasons for that we're not going to get into. But if n is greater than 1, then it's n times n minus 1 factorial. So what we have here is what we call in mathematics an inductive definition, right? How many of you have come across inductive definitions before? A couple of you. Very few of you. You guys must be in math or something, right?
Engineering.
Engineering? Close enough.
Close enough.
So, inductive is, it's like you get into like these interesting situations in mathematics where like it's very convenient to define something using itself. In any other field or discipline, that would be called circular reasoning, which is something that you don't want to do. Like obviously you don't want to define a word with itself, that's stupid. But with mathematics, if you set the conditions very precisely, you can actually get away with it, which is what an inductive, that's what an inductive setup is, right? So the reason they call it inductive is because it uses induction, which some of you maybe have heard of that term. So essentially, if you come across anything with an inductive definition, it's very easy to solve it with a recursive algorithm. But we're not going to talk about recursion for a couple of weeks. But I just want to put that word in your brain that that's a thing we're going to come back to is recursion. But let's do a couple of straightforward implementations of factorial just quickly, and then we can get it a little more complicated. So, very, very simple loop, right? I wish I had like a, is this rigid enough to use the point and stuff? Let's see. There. So, factorial function, right? I is 0, f is 1, while I is less than f. I plus equals 1, so that's the counter, right? F is equal to f times I plus 1. This is what we call the accumulator, right? So this is a very, very common common setup for loops, which you'll use and see an awful lot once you get into programming, like the assignments, assignment 2, etc. Assignment 2, things are going to get harder from here, folks. Assignment 1 was what you call child's play compared to what you're going to be expected to do by the end of the course. So, hello, come, get a seat. You're cramping my style, man, come on. So, the accumulator accumulates what will eventually become the final value of the output. So basically what we're doing is we're taking a segment of memory and we're saying this is eventually going to be the result, but it's not the result yet. We're going to perform the calculations we need to do, store the intermediate results inside that memory cell. That's what f is, right? So f is going to be the factorial, that's why it's called f, and that's why we return it at the bottom. So, it's fairly straightforward, right? So the thing about, so essentially as you're going through this loop, every time you iterate through this loop, you're multiplying into f the progressively larger values of I, which is what eventually calculates the factorial for you. Any questions about this so far? Fairly straightforward? So good to be able to see people nodding. Yes?
Sorry, this might be a really dumb question, but where you have your definition of factorial, is this actually a program with these commas, or are you just explaining it?
This is the mathematical definition expressed as a formula. This is a completely whole and valid Python program that calculates it. I mean, and down here it's being used on 5. So if we go through this, right, if you sort of sample the program at lines A and B, right, when you hit line A, we have an initial value for I of 0, an initial value of f for 1, right? Can anybody tell me why f doesn't start at 0? No, you're the TA. And you already, you there, in the black mask.
Like anything times 0 is 0, so like it would work.
Right, so if we initialize that to 0, then we wouldn't get anything as the output because you'd be multiplying 0 by 0 by 0. Well, it'd be like 1 by 0, 2 by 0, 3 by 0, etc., etc. Right? So, good. But you'd be surprised how often stuff like that catches you when you program, right? So you need to be like, the essence of programming is paying attention to these tiny little details, any one of which will completely destroy your algorithm. Like, it's attention to detail. That's the essence of programming. But as you can see, by the time we've reached the 5th iteration of the loop, f has reached the value of 120, which is the final return result of the factorial function. Any questions? Yeah. Right, yeah, so with these guys, and yeah, you're right, that is kind of a point of confusion. I don't recommend using multiple assignment at your level. It makes it fit on the slide, I guess. I don't know. But yeah, this I plus 1 will take effect independently. You can think of it as happening after, but they're both having the same. Essentially, they both happen at the same time, but they can't see the result of each other's calculation until both are finished. That make sense? Yeah. Question?
When I tried to run it, it said f is not defined.
Yeah. Yeah, that would be correct. Yeah. That's because this thing's out of scope in this context. Yeah. Well, the print statement should be around the factorial, the call to factorial. I don't know why it's like that. I had some people redo translate the slides from PowerPoint to LaTeX a few years ago, and I haven't had the time. Oh wait, there we go. Never mind, they knew about it. Okay. So, anyway, so you're exactly right. F is not defined in this context. we're going to talk about something called scope. Scope is a very important concept when it comes to programming. Certain variables are only defined in certain contexts. So I and f are constrained to the context of the function in which they are created. When that function is no longer the thing that is being executed, they are destroyed. Now there are very technical reasons for this being the way that things work that you'll learn about if you take 1xc3. They'll get into what the function call stack is. The Coles Notes version. Inside of your computer, there's a piece of memory called the call stack, which keeps track of all the functions that are being executed. Inside the call stack itself is where local variables are actually stored. When a function is terminated, it is removed from the call stack, and anything that it contains, contained in that stack frame is also destroyed. So these guys are actually deallocated memory at the end of the execution of that function, which means they no longer exist, which is why it doesn't exist down here. Basically, hopefully everybody has gotten to the point now where they understand defining the function is different from executing it, yeah? Let me see some nodding heads if you get that, yeah? Okay, good. So this is where you actually call the function. This is where you actually get your output, right? Or you're actually executing the function here. So essentially, the execution of the function is contained within that statement. After that statement is finished, the function is deallocated. In fact, all it's really doing, the lifespan of that function is only so long as it takes to get to one return statement to get some concrete value out of the function. After that point, that concrete value is substituted wherever this guy is in the code, and then you just continue as normal. So by the time you get to the print statement, the printf, f no longer exists. All right? So this is what we call a local variable. We call it local because it's local to the function. The opposite of a local variable is a global variable. A global variable, which we're going to see in this slide set, applies for the entire script. So the script may define several functions. The global variable applies for all of them. Any questions so far? Good? Yes?
I don't see if it has if we took out the first line of the variable to define out of the function, then would that last statement work?
Not quite. You can, that is the way to declare them as global variables, right? You could take these up here, right? But in order to be able to use them in the function, you also have to declare them as global variables in the function itself using the global keyword. So yeah, it's possible to do it that way, but it's also not recommended for a number of reasons, right? So let's think about the situation where these might have been global variables, right? What happens so let's imagine we take this line of code and we pop it above, right? What happens if you run the function twice?
It will give an error.
It will not give an error. Yes? Precisely correct, yes. So the function is happy to run, but it'll run with the output result, the final values of I and f from the previous run become the new initial values for I and f on the next run. So I think if you actually did it, it would be what you would actually see as output is any call to a factorial number that is greater than the one that you had previously basically would just continue the loop until it hit the new larger value of n in this loop. But any factorial number that you tried to calculate factorial for that was less than the previous one would output for you the factorial of the last factorial that was calculated. Because what will happen is let's say we run this on 10 and then we try to run it on 5, right? So in the final analysis, I is going to have a value of 10. So if you start this up with n equals 5, you hit this condition, right? Is 10 less than 5? No. So the loop never executes. So the value of f that's returned will be the value of f from the previous iteration, or the previous call of the function. Make sense? That's a good question. So, awesome. Let's see how you're doing. Yeah. So, without multiple assignments, it's less compact, but again, this is definitely the more preferred way that I would like you guys to be programming at this point. Please feel no obligation to use multiple assignment. It just complicates things without really adding any benefit at this level, you know. Frankly, I'm not sure that it adds benefit at any level, but it's Python, so, you know, Python will do what Python will do. But yeah, so you can see all that we've really done here is we've teased out the two multiple assignments and split them into two. Now, there is one thing though. Who can tell me the difference? Yeah.
Like in the while loop, those two things aren't happening at the same time anymore.
Right. That's a semantic difference. But what about the way that the lines have been written is different? Yeah.
One is more readable.
Well, yeah, that's true, but that's again, like, okay. So notice you've got f times I plus 1 here. Here you've got f times I, right? That's because the I plus 1 has already been put in place, right? That's already been calculated, so you don't have to put I plus 1 here because it's already been plus 1, right? Make sense? Good. So, one thing that I want to reinforce about all of these different things, all of these different examples, we're about to go through like 4 or 5 different examples of ways that this algorithm can be written. It's very important for all of you to understand that the way that you write an algorithm is likely going to be specific to you, right? It's like writing an essay. Even a very, very simple algorithm will have 10 ways to do it, more than that. I often say that, like, for any particular algorithm, there's at least 100,000 different programs that could solve the problem, right? So, basically, if any of you were thinking, you know, oh, you know, it's okay if I use my friend's solution to one of these assignment questions, because, you know, there's only one solution to it anyways. It's like, no, we'll catch you and you'll be prosecuted for academic dishonesty. Absolutely. So, even aside from the fact that, so here's another one, right? These two are semantically identical, but this just demonstrates that if you want to put more than one line on one line in Python, you can separate them with a semicolon. In most programming languages, semicolons are used as your general purpose line termination character. So all lines in C, for example, have to have that semicolon at the end, or else it's not syntactically valid and it will not compile. But in Python, it's just used if you want to put more than one statement on the same line and separate them. Like, you know, you could write your entire program on one line if you really wanted to, but it wouldn't be readable, you know. Readability is very important. Any questions? Good. So the decision to start multiplying with 1, 2, 3, etc. is actually arbitrary. You can actually start from the top and work down as well, right? So these are the tiny little decisions that programmers make every day of their, you know, every minute of their lives that make their algorithms different from everybody else's. You can count down from n to 1 just as easily as you can count up from 1 to n, right? It makes no difference because, of course, multiplication is commutative, so, you know, from a mathematical perspective, it doesn't matter what order you do the multiplication in, but, you know, perhaps I'm beating the dead horse. But yeah. So the other thing that you could do, which is kind of like, it's kind of like vaguely not recommended, but you know. The function's parameters themselves can also be modified if you want to. Notice in this case, rather than declaring a separate variable I, we're just modifying n in the manner in which, you know, makes the algorithm work. So Python uses a style here, like a semantic stuff. You guys know what I mean when I say the word semantic? Who doesn't? No shame. Yeah, okay. So, in languages generally, right, there's a difference between the syntax of the language and the semantics of the language. The syntax is the grammar, right? It's how you put the sentence together to form sentences, you know, conjugations, verb agreement, all of those things are rules of syntax. Semantics is what it actually means, right? So when I say semantics, in this case, what I'm actually, like, I'm kind of being a little sneaky, because what I'm actually talking about is the way in which this is going to be interpreted as machine code, right? Because the CPU itself runs on different instructions than these, right? This is not what gets executed on the machine itself directly, right? If you want to learn more about that, take a course like 1xC3, which gets into C program. This gets translated into machine code. That's the process of compilation or interpretation in the case of Python. But yeah, so there is a underlying semantic here, which is called pass by assignment, which is actually fairly idiosyncratic to Python itself. Essentially, n is a variable, and it's isolated from the rest of the program in Python. So you can use it like it's a regular variable. It's not necessarily the best way to code, but you know, in this class, it's kind of the standard is kind of if your code works, then that's good enough, you know, because you know, it's a lot. I know it's a lot of information all at once, but it's interesting though because with pass by assignment, as we're going to see, there are some interesting things that happen with assignment operations once you start getting into mutable data structures. And like the important part to remember is that when you pass a mutable data structure in, it gets like the same rules of assignment that we are going to talk about also apply to anything that you pass in by an argument. And you know, we can explore we can take a look at that at some point. But good. So, yeah. So, another very important thing to note, which sometimes trips up beginners. This guy right here, isolated from x. The value of x will not change, even though n is being assigned to here. That's what pass by assignment means, right? It's like it's creating a new variable, assigning it the value that's passed here, and not touching this guy any further. That's the decoupling that occurs with pass by assignment. So if we were to print x here, we would get 5, despite the fact that n has been modified by the algorithm. Make sense? Good. Excellent. So, yeah, I talked about that. I recommend against this approach of modifying a function parameter. It can be hard to remember when it will result in a change outside the function and when it won't. Basically, that's a caution. That warning is about dynamic. No, what's the word for it again? Mutable. That's a warning about mutable data structures. A mutable data structure would be modified outside of the function call because that's what mutability means. But you know, we don't have to get into it right now. So, good. So, counters and accumulators. All iterative implementations of Factorial use an auxiliary counter variable to keep track of how far along we are, and an accumulator variable, which becomes the result. I already went over this, but of course, I was the counter, F was the accumulator. I was the counter because it was counting. Very, very simple. It goes 1, 2, 3, 4, 5, etc., etc. The accumulator accumulates the correct answer. I know it's like weird to think of a correct answer as being accumulated, but you know, that's the way you have to think when you're programming, right? So, counting can go up, counting can go down, counting can go by twos, counting can count like any way that you can count. The computer can count faster. So, basically, the accumulator has to be initialized to a value that is the correct result if the loop is not executed at all. That is a most common error. Again, that business where if we're calculating factorial, you got to initialize it to 1 because that's the base for multiplication. So, good. Question: what does this code output? I'll give you a minute to look at it. Man, it's really hitting me how much better these slides are designed for an in-person class. So, what do you guys think? How many people think A? How many people think B? How many people think C? How many people think D? How many people want to go get a sandwich? Yeah. So, the correct answer is D, oddly enough. So why? Why doesn't this thing output anything?
I can try.
Yeah.
Okay, so if my input, is that T at the bottom, my input or no?
Yeah.
Yeah, so let's say we've input the 5. Well, I is less than the length of T. Oh wait, I is 0.
I is 0, and the length of T in this case will be 3.
So it's less than the length of T.
Yeah.
And then S is we add I to T.
Nope, this is indexing.
Oh,
Right?
we get the index of
Yeah.
what I.
So the
if
first
I is
iteration
0.
will pull this guy up, so it'll be 5.
Yeah.
Yeah. Does this change your answer?
No, but I thought it was doing something else.
Okay. Yes. Yeah. So this algorithm is missing a crucial step, right? I is not being modified. Because I is not being modified by this loop, it's basically, if you were to run this thing, it'd be like, is I less than 3? Yes, do this. Is 0 less than 3? Yes, do this. Is 0 less than 3? Do this. Yes. And a computer is stupid enough to do that actually forever, right? So, very easy fix. All you have to do is say I equals I plus 1. Right there, fixes the algorithm. But this is what we call an infinite loop. Infinite loops are a very common class of error that you find in programming. Very easy to create them accidentally. They're a big novice trap because you forget stuff like that. Frankly, you'll probably see me write a loop where I forget to increment the counter at some point, because I'm just I'm a bit of a scatterbrain. But it's kind of two ways that infinite loops come at you. One is like a beginner way, where you just forget that step. The second way is actually when you're an intermediate programmer and you've just made your loop so complicated that you don't know where it ends, and you forget to put the ending in, right? So you can also end up with an infinite loop that way. But generally speaking, how many here are Windows users? Yeah. Mac users? Linux users? There we go. Yes. So in Windows, you know where, you know when you get a program that like grays out, and it's like we are waiting for this program to respond, and you know how it's always a trap to wait for it to respond because it never does? Infinite loop. And almost every time that's an infinite loop. It's either an infinite loop, or like they forgot to have the thing communicate with the operating system for like 5 seconds, you know? But yeah. Anyway. So, infinite loops are like, depending on where the infinite loop occurs, it can actually crash the computer. Most of the time the operating system will handle it, so you don't have to worry about it. But if you get one that happens inside of like a Jupyter environment, or if you have one that occurs in a command line that you might be running, the only solution is to just to terminate it. So in terminal, that's Control-C, and that's like, you know, if you're using Windows subsystem for Linux or something like that, that guy knows what I'm talking about. Otherwise, there is a, you know, it'll tell you whether your thing's responding right here. You can hit stop right there, right? Otherwise, you have like, you can also shut the server down, which closes all of your notebooks, which will also kill any loops that are infinite. But it's not, you know, it's not sufficient just to kill the loop. You also have to fix it before you run it again, or else you'll just be in the same situation. Yeah. Any questions? Good. So let's talk about typecasting. Sometimes you have an integer and you want a float, or you have a float and you want an integer. In Python, it's very simple. You just enclose the thing that you want to convert to another thing in the name of the thing you want to convert it to, used like a function, and that's all you need to do. This is actually a very versatile. This is a very versatile way of doing things. You can convert tuples to lists and back again. You can convert a list to a string, although it leaves in all the brackets, so you probably don't want to do that. But has that icon been there the whole time? Can I move it? Get out of here. There we go. So yeah, it's like the syntax for that is very, very easy. It's just you know, if I have a tuple, it's as simple as that. So we've talked about if statements at some length. I believe in online I touched on the idea of the elif. So you know if statements. You may even know the if-else statement. But do you know the if-elif-else? It's very simple. You just take the no branch and you put another if statement on it. That produces the if-elif-else. You know, you can actually have as many of these as you want. You can keep piling more if statements on the no branch, and you can just include more else cases. Now, it is 110%. You can just do that with ifs and elses. You don't actually, like, this is not a requirement that you use elif, but it does make your code a little bit more compact. It means you have less indentation, and that might be nicer looking. You know, else if is kind of like a generally understood construct in programming. You know, so it is what it is. But yeah, so If condition B comes out true, you execute S. If it doesn't, you try for C. If C comes out true, you execute T. If it doesn't, you fall through to the catch-all case at the end, and you execute U. Any questions? Yeah.
Can you just use like only ifs, or does it have to be if this, else if this?
Is your question what would happen if you put an if here?
What would
Yeah.
happen?
Yeah. You lose the exclusivity, right? So you have the condition B, right? The whole rest of this hinges on B coming out false, right? If you were to replace this with a regular if statement, then you would, if B, you would do S. And then regardless as to whether B was true or false, you would then test C to see if that was true, and then if it was, then you'd execute T. Right? So it decouples it from the first clause. Any other questions? You're gonna have to shout though.
What would happen if you forget to put the else in it?
Like just if, elif,
Yeah.
there would be no catch-all. It would just, you would go through this one, right? You would then go through that one, and then there would be just no catch-all. So there would be no, so if you unindented U and just removed the else case, you would do all of this stuff, and then you would always do U at the end regardless how any of these came out. Make sense? Any other questions? Yeah.
So elif is like basically a second if, like adding another boolean to this program.
Yeah.
Okay.
Yeah. It's kind of like one of the ways that these things are often used, right? Is let's say you had some variable that you wanted to test. It could have several possible values, right? So a pretty common thing is if x is equal to 0, do something. L if x is equal to 1, do something else. L if x is equal to 2, do something else, etc., etc., right? Now, you could make the argument that you don't actually need to use elifs here, but the problem that it answers is what if x is modified in here, right? Right? So let's say you were trying to have different cases based on the value of x, right? But let's say that at the end of this you set x equal to 2, right? If you just use else's, you would activate both of these conditions. But if you use else ifs, even if this gets modified, you still only activate the first condition, right? It's exclusive. This one has to not go through in order for these guys to be considered, regardless of as to what happens in here. Make sense? Any other questions? Yeah, you're gonna have to shout.
When you use if and out those statements, can you have multiple return statements?
I mean, you could use multiple return statements. Generally speaking, it's discouraged as kind of bad practice, but again, I'm not really super concerned about practice with you guys. If you can get the algorithm to output correctly, that's good enough for us, you know. But yeah, if you wanted to, return, you absolutely could use multiple. In that example over there, you could have multiple return statements inside of each one of those cases. Absolutely. So this kind of gets into a broader stylistic point, though, which is what we call spaghetti code, which is a very old term that dates back to the use of primary when programming languages were pretty much exclusively assembly languages. It turns out that if statements and while loops were at one point an innovation, right? The early programmers only had a kind of a construct called a goto, So the way that a goto works, and I really shouldn't be showing this to you because it's like black magic, but this is what a goto is, right? You would have like some statements. You would have a label in the code, and then down here you would have goto A, and you can have like conditional gotos as well, and this is how it still works in assembly programming. But this just puts execution back to wherever the label is. And you can do this in C programming actually still to this day for some gosh darn reason. But essentially, it is possible to write programs that are completely impossible to read using goto statements. That's generally what's referred to by spaghetti code. Spaghetti code is still a problem, but it has been it's been improved considerably since the entire programming community decided to lock this particular piece of elder magic in assembly language, and nobody is to speak of it. So, you know. But yeah, like gotos are actually extremely useful if you're doing like really fine scale optimization, because you can get constructs with gotos that are impossible with if statements and while loops, or loops in general. Conditionals and loops. Anyway. So yeah, the reason they call it spaghetti code is because like the strands of execution sort of loop in and around the program like it's a great big ball of spaghetti. So when you're looking at the program, all you're seeing is intersecting threads, and you're not seeing its, you know, a beginning and an end. That's why functions are recommended to be written as we recommend that you write them, because you have one entry point at the beginning of the function and one exit point at the end of the function, and that means that you can always know where it starts and where it ends. That's, you know, if you're using multiple return statements, that means that you have multiple possible exit points to that function, which means that, you know, you can't be sure that any one of them will be the one, right? So yeah, that's kind of why it's recommended as a sort of a stylistic concern. But yeah, so we're going to explore an algorithm that tells us whether or not a number is even or odd, which is, you know, not terribly interesting, but, you know, here we are. So, everybody remember our good friend modulo? Good. So, modulo is the remainder of integer division. So, if the number is even, the modulo will be equal to 0, otherwise it will be equal to 1. So, if n mod 2 is equal to 0, return even, else return odd, right? So, you know, fairly standard algorithm. But what if we wanted to make it more complicated? What if we wanted an algorithm that would tell us whether 2, 5, or 10 is divisible, or pardon me, if a number is divisible by 2, 5, or 10? So, how about this guy? What does this guy output? I'll give you guys a minute. So how many people think A? How many people think B? How many people think C? Cool. So, let's trace this through. So we're calling divisibility with 5, right? So we put 5 in place for n. Is 5 mod 2 0? No, it's 1, right? Is 5 mod 5 0? Yes, because 5 divides itself evenly. So we return by 5. Next call. Divisibility 10, right? So n is 10. N mod 2. What is n mod 2? Or what is 10? What is the integer division? What is the remainder of integer division if you divide 10 by 2? Yes.
Zero.
It's a big fat goose egg. So this actually passes. So we get by 2 as a result. So the answer is actually A, which is not what we want, right? But like, and this kind of hinges on the idea that there's like an implicit consideration embedded inside of the problem's description, which is not really made it's not made explicit, but the idea is if it's divisible by 10, that's more interesting or important information than if it's divisible by 2, right? It's more specific. It's more specific to be divisible by 10 than by 2. However, anything that's divisible by 10 is also divisible by 2, because 10 itself is divisible by 2. So technically this is correct, right? But it's still not what we want. Yeah?
So if we exchange the place of modulus 2 and modulus 5, so it first goes as n modulus 5. If it's equal 0, return by 5, and then elif modulus 2. If it's equal to 0, return by 2. Then it would be 5 by 5.
Yeah.
So that's just, it's become 5 by 2 because 2 comes first and 5 comes second.
Yeah, absolutely. So if these two cases were switched, you would get by 5 by 5. Yeah.
So as long as it works, like if your return value doesn't matter what the next comes after, it works.
Yes. It always takes the first one that works. That's how an if statement works. That's how one of these works. That's like the essential truth I'm trying to convey. So thank you.
And like if it's once, like it doesn't matter the next one, you mean? Like
No, yeah. So yeah, like even if these weren't return statements, like for the 10 case, it doesn't even test these. Right? It hits this one passes, and it's done. It doesn't care about these ones. That's the nature, that's why they're exclusive cases, right? That's why it's else, if, right?